Hello and welcome back to HK Academy. Designing a Type 3 compensator is usually taught as a manual process. Place a pole here, a zero there, simulate, adjust, repeat. In this video, I want to show you a different approach. Instead of manually tuning poles and zeros, we let an automated script design the compensator for us, based on a desired crossover frequency and phase margin. Using GNU Octave, we formulate the compensator design as an optimization problem and automatically compute the type 3 parameters for a buck converter. This is not a replacement for theory, it's a practical tool that builds on it and dramatically speeds up real world control design. This script performs a high precision numerical optimization to automatically compute the four unknown frequencies of a continuous time type 3 compensator: the low frequency pole omega p0, the two phase boost zeros omega z1 and omega z2, and the mid frequency pole omega p1. The highest pole omega p2 is fixed at half the switching frequency, which is a standard and very practical design choice. The goal of the script is very simple. Find the exact pole zero positions that make the loop gain cross unity at the target crossover frequency with the target phase margin, and the user only needs to provide the small signal plant parameters, the feedback gain, the PWM ramp gain, and the desired crossover and phase margin. Everything else is handled automatically. The script begins with a section where the user enters all necessary converter parameters: DC gain of the control to output transfer function, ESR 0, LC damping factor, and LC resonant frequency, and the control specification where we have the feedback gain age, PWM modulator ramp, desired crossover frequency, and desired phase margin. And you also define the switching frequency, and from the switching frequency, the highest compensator pole is here calculated. This ensures good high frequency roll off, predictable noise filtering, and stable digital implementation. Next is the GVD eval function. This function evaluates the small signal model. This includes the ESR0, the double resonant pole, realistic LC damping, exact plant phase behavior, and this is the heart of voltage mode control design. The function GC eval evaluates the type 3 compensator. This includes integrator for zero steady state error, two phase boost zeros, two high frequency poles, and fixed second pole at one half of the switching frequency. For remaining unknowns, the script must compute. For any candidate, pole 0, set omega p, the script computes the loop gain. It then sweeps a frequency vector from 100 Hz to 1 megahertz. It computes the loop gain magnitude. It finds the unity gain crossings, computes the phase margin and crossover. This is stored at FC and PM. FC is achieved crossover, and PM is achieved phase margin. A type 3 compensator must obey following conditions here. So omega p0 must be less than omega z1, omega z1 must be less than omega z2, omega z2 must be less than omega p1, and omega p1 must be less than omega p2. If this ordering is violated, the script adds a huge penalty. In this case, 1 to the power of 6, which is forcing the optimizer to search only within physical meaningful compensator structures. This ensures a stable compensator shape, predictable phase boost, no inverted zero pole ordering, no invalid transfer function behavior. This is critical for reliability. The script also computes the mismatch between achieved versus desired crossover and achieved versus desired phase margin. The optimization engine fmin search tries to minimize this cost, meaning the loop gain must cross unity at exactly your target frequency. The phase margin must be exactly what you requested, and this is the central intelligence of this script. fmin search works extremely well for this problem because the cost function is continuous. Gradients exist naturally. There are only four variables to optimize. The ordering penalty helps guide convergence. The loop gain shape is smooth and convex like. This often converges to 1 to 3% error approximately, and for well damped system, often well under 1%. The script here prints all type 3 pole 0 frequencies, the achieved crossover frequency, and the achieved phase margin. This gives users a clean and confidence inspiring summary. Here is also section B, which is an optional section, and this part makes the script extremely user friendly because it plots GVD of S magnitude and phase. It plots GC of S magnitude and phase. It plots loop gain magnitude and phase, and it computes custom stability margins. If you only want the pole zero values, you can remove the section B. But let's now run the program. First, what you can observe here is the body diagram. We can make it a little bit bigger. And here is the marked what is the crossover frequency, and we can observe it is very close to 10 kilohertz. And here is the phase margin, which is also approximately from here to here 70 degrees. We can click here, and here we can observe what are our calculated poles and zeros for optimized type 3 compensator, what is the calculated crossover and the phase margin, and these are the values which we read from our body diagram. We can make one more example. Instead of 10 kilohertz, we can put, for example, here 7 kilohertz with the same phase margin. And if we run it again, here is the body diagram. Now you can observe that it's shifted. So if you want, we can zoom it, but it's not necessary for now. And here we can now observe the new values for our compensator. And here you can see the around 7 kilohertz, it's crossover, and 70 degrees phase margin. This method using automated script has several major advantages. It eliminates guesswork, it produces repeatable results, it is independent of the specific converter topology, it works for any plant where the small signal model is known, it is extremely accurate, often with 1 to 5% of the target specifications, and most importantly, the results come in seconds compared to hours or days of manual tuning. This tool saves enormous amount of engineering time, especially when designing converters with multiple operating points. This automatic script not only computes the compensator poles and zeros, it also plots the loop gain for verification. If you would like to experiment with yourself, I have made the complete Octave script available as a free resource. You can download it together with a detailed README from my website. The link is in the description. And if you want to learn how to design Type 3 compensators manually, understand every pole and zero, and implement them digitally on TIC 2000, that's covered step by step in my Type 3 compensator and buck converter digital control courses. Thanks for watching, and I will see you in the next video.